Christoph Fenyvesi, the Chief Executive Officer of International Symmetry Association, and this is my great pleasure to welcome you at the Vienna Lecture Series, where we will have the talk from our distinguished speaker, Professor Haresh Lalvani from Lalvani Studio and Pratt Institute, New York. I would like to ask the honorary chairman of our association, Dr. György Darvas, to introduce Professor Haresh Lalvani for us. Dear György, please.
Ladies and gentlemen, I will tell a short laudatio before the lecture of Haresh Lalvani. Professor Haresh Lalvani is a tenured professor of architecture at the Pratt Institute. Easy to read, such where he is also the director of the Center of Experimental Structures. In 1993, Dr. Lalvani received the Pioneers Award from the Space Structures Research Center, University of Surrey, United Kingdom, for his distinguished contribution to the field space structures. This year, he received a Cosmic Fishing Award presented by the Synergetics Collaborative, SNEC. For those who don't know what is the Synergetics Collaborative, this is an association which continues the heritage of Robert Buckminster Fuller. And the SNEC RISD symposium and is which is the highest honor given by SNEC as an acknowledgement of lifetime merit in the field of design science. I apologize because my eyes are not the best. And internationally recognized architect, morphologist, and an artist in vector. He has worked at NASA Langley Research Center on space applications and at the pioneering computer graphics laboratory New York IT on computer animations and before computer-centered architecture in the 90s. He was an artist in residence at the Cathedral of St. John the Divine, New York, for a decade. He has collaborated across different fields: computer science, engineering, dance, theoretical physics, in accord with the pendisciplinary scope of the work, which includes establishing an international standard in telebiometrics. A recipient of grants from NASA, New York Star, NEA, Graham Foundation, and other agencies, Professor Lalvani is the author of 2 self-published books, Transpolyhedra, 1977, and Structures on Hyperstructures, 1982, the latter based on his doctoral work in architecture at the University of Pennsylvania. He has published there landmark articles in architectural design, where he was cited as a seminal figure. He has numerous morphological discoveries and patented inventions to his credit. He is the inventor of the algorithm with uppercase A and uppercase R, and XURF product lines developed in a long-term collaboration with Migo Burkin, a leading architectural metal fabricant in New York. His solo show at Design Miami 2011 was a mini sensation, and his work was a top pick by some curators. He was a speaker at TED 2004, Monterey, California, and TEDx Brooklyn, New York in 2010. His algorithm columns are in the permanent design collection of the Museum of Modern Art, New York, and his recent sculptures are permanently installed in public areas in the streets of New York. This was an official laudation, but I would like to add a few personal words. Haresh Lalvani and me knew each other for nearly a quarter century, and we met the first time personally in 1995, first in Washington DC, or near to Washington DC, then I was the guest of Haresh Lalvani in New York. I have many best memories of New York, but which made for me the deepest impression was when a day Haresh invited me to the New York Cathedral, which was at that time still under construction, and he was commissioned to decorate the entrance or around the arc above the entrance, not by saints but with polyhedra. The most impressive was not this. He had a small laboratory, a long cell at the second floor, cell built in the walls of the cathedral, and he showed me his secrets. The official foundation didn't speak about that. He showed me on the walls the sketches of his periodical table of polyhedra, which was very impressive, and I think it is as much important in his career like his design works, which is now very much appreciated in the world. But in these circles where scientists, artists, designers are together, we should mention the periodical table of polyhedra developed by Haresh Lalvani as well. I would like to add to the two books which were mentioned in his biography. This book, published by J. Kaproff in the early 90s, on whose cover there is a design made by Haresh Lalvani. And I would like to mention a recent book which was published 3 years ago by Haresh and contains a very good selection of his works. And I would like to cite a work. This is a public sculpture, probably you will show in your lecture, and you added to this large sculpture that C54 has a new geometry. We don't know yet if it exists in nature. Maybe someday it will, with or without our help. And I think this is very important for us. And I will too long and will not mention that there are among his works sculptures as well, and I hope he will speak about those, which can be used as models of singularities in strong gravitational fields as well. So I give the floor to Haresh Lalvani, please.
Thank you. click on.
Is this on?
Yes.
Yeah, okay.
Okay.
Okay. György, thank you very much for this introduction. He's taking me to the past, and it always makes you very pensive when you have to think about your past, because you're sorting so much out. And that brings me, so then I must put this in the context of the past. In the 70s, I was going to science conferences, and in fact, major ones are Cold Spring Harbor Lab, which is, as you know, Watson's place. And he was very kind enough to sometimes invite me there, and you watch the scientists, and the idea struck me at that time. How is it possible that the seemingly infinite variety of forms we see in biology are just manipulated by 4 chemical alphabets? I still can't understand how it's conceptually possible. Yeah, we see all the genomes being decoded and all that, but it raises a question for me. You mentioned the periodic table. In chemistry, every student of chemistry learns the periodic table of chemistry. You're told right on day 1, 118 elements, maybe some more, that's it. Everything comes from that. It's, for us, outside of science, this is mind-boggling. Everything in the universe, all matter, not just us, not all these objects, us, 118. So clear question, and artists are taught 3 colors, red, yellow, blue, in pigments, or the RYB, the RGB system. That produces all the colors. It's incredible. In design, is there an equivalent for form? We don't have an answer. Unsolved, open question. So the question is, what is the underlying palette of form? And my focus is really the last part, form making. And the terms thrown in are inspiration from biology, but genetics I would use in sense of a formal coding of form, and epigenetics, which, at least for the moment, lies outside of that. So those are and the question it raises is, what is the origin of form? I don't know the answer. But I speculate that it probably comes from numbers. I'm not sure, but I'll try to make a case. So what I do is I look at numbers, and numbers are highly organized, and I try to tame them in some ways. How can you make some sense out of this? So what's happening here is, oops, I'm sorry. I wanted the pointer. Okay, what's happening here is you can, if you take this up to 9, let's say, and do the decimal system, you can go from 1 to 9, and you take this one, you can go up to 99, you can go to 999, and so on, and you can keep going to infinity from digits 1 to 9, and you'll get the entire decimal system in one space. Now, if you assign a meaning to number, then clearly, in this case, formal meaning, in terms of shape, then the expanse of shape becomes this infinite space of numbers. And so that's one of the ideas I'll be using as an underlying driver for this work. But it's more complex. For every number, you might find more than one shape. Then the universe of shapes becomes larger than the universe of numbers, by definition. I'm not sure, but... And the other feature of this work is... can you... That's my son Zara, he's trying to help with the animations. This is a 4-dimensional cube, which is morphing. And in fact, you don't see, because of the lights, that it's really tracking itself on a 4-dimensional cube. So it's moving on the vertices as it's adding and losing dimensions. This is the spirit of rest of the work, meaning 2 ideas here. One, there's a continuum of formal possibilities. Second, that every structure has an underlying structure, like a metastructure, which in this case is self-similar because you're taking a hypercube and you're mapping it on an underlying hypercube. But in general, form has metaform, and there's a kind of a self-similarity. So that's the thesis. So I'll start building up from regularity, and this is well known to all the people here in the audience, but let me make a case here. Every number can be associated with the shape. I'll start with regularity because that's the way I started the work, and it's so in part sense chronological for myself, but maybe it is a starting point. I'm not sure. I'm still questioning this. And in the space between the numbers, what's happened between 2 and 3 and 3 and 4, you can either fill them with real numbers or you can fill them with fractional numbers. I'm showing fractions, so that if that is a triangle and that is a 4, in between it, everything between 3 and 4. So these are the stellated polygons, or if you want to change in terms of if polygon is p-sided, then you can argue that this is 3.3 sides and it's 3.67 sides, etc. And then if you add a second number to it, which is, as you know, valency, the Schlafly symbol, then the space from one dimension becomes an infinite two-dimensional lattice. And if you add a third dimension, you get the four-dimensional polytopes, and these then become, I mean, you know the Schlafly symbols, so this is nothing new for you. But the idea here is that these are also the Cartesian coordinates of the space, so that every polytope, it has a location in space. And this one will continue here with more direction. In fact, you can go all the way, and this space, for every place there is a possible shape. So then what you do is, what I'm going to show is a systematic, kind of quasi-systematic, because I'll build up, and I'll be adding dimensions to it, and then I'll keep like a dimensional clock, so that's the dimensions of space we're going through. Here what I've done is taken the PQ, the two-dimensional, and then there's a 3, add to this 3 more. So you start with the origin here, you go there, you go there, you go there. So this one is 1, 0, 0, this is 0, 1, 0, this is 0, 0, 1, and then this one is a combination of this and that. So in fact, and this one here is a combination of those two, and that is a combination of those two, and all 3 are this one. Now, this is simple combinatorial work, but it's more interesting than that. If you take the measure, the geometric measure, then if you take this object, for example, which is a truncated octahedron, and you take the distance from the center to the square face, and you take the center of the cube, this is a cube, this is face on, those two distances add up to the insphere of this to the center. Likewise, this plus this will add up to that, and this plus this adds up to that, and the opposites add up with, yeah, and this plus this will add up there, this and that. So there's the fundamental complementarity here. And it is supported by the metric measure, and also if you calculate the topology, it's supported by that, because what's going on is, as you go here, you're gaining topology, and in the opposite direction, you're really losing topology. And what's been gained on the other side in one direction is lost on the other side in the opposite direction. So that's the fundamental nature of, I think, for form as a kind of a thesis, if you wish. And same thing applies to prisms. And here, sorry, can you show this? And then if you look at them in a continuum, like the hypercube we saw, you'll see a continuous morphing, but it's completely analogous. So then what happens is, in this very simple case, you know all of these things, but I'm trying to present a global picture. That if you have one location and you can, you know what it looks like, you can easily predict over the entire space. So actually, there are 3 dimensions here, there's 4th this way, and 5th this way. So the entire regular and semi-regular polytopes, not counting the snubs, fall into a 5-dimensional infinite lattice. And if you look at the Schlafly symbols, those numbers become very dense and very complex. And a thing like this, for example, is 4 pentagons around a vertex and so on. And these are semi-regular. And you start to see you're walking through this infinite density of these symbols. So here's some pictorial representation of all of these. You will be seeing that I have 2 directions, and this plane is, all of these are 100 objects, and those are the Schlafly symbols. And then I'm going to take this plane and start moving this plane around this cube. And you'll see it's like taking an infinite lattice, moving it on through a cubic space. Nothing really new here, but accepting is packaging it. And this is what it looks like for that particular case. And duality is a little bit, and then you can take that whole 5D lattice and do the duals of them. And I put a question mark here. This is mostly for me because my mind is made up, because I found 2 different ways to find this. Haven't settled my mind which one it is, because it can go from every object can explode to intermediate and then implode, and you get a dual as a continuous process. Or that duality itself is one of 4 possible operations. I'm not sure about that. And then you can get more complex forms. For example, in this case, again, this is all familiar to you, that you add 2 more dimensions to the space, and you get subdivisions from mirror symmetric over here and along the diagonal to all the skewed cases here. And these are familiar to you from viruses and buckyballs and so on. And buckyballs are essentially duals of this. And so if I add one more to this, I add the full yellow color, which is all the rhombic tessellation, then I get all these hybrids. And I get a set of 16. Again, the complementarity I was talking about will work here, where the sizes, metrics is this plus this will be equal to that plus that, that plus that, and so on all the way through. So that these numbers then start to have a meaning. So if there's a 1, 0, 0, its complement is 0, 1, 1, and so on, and it'll reflect in not only the metric, but also the topology of the structure. Some illustrations are one class of those, or the entire set here, and then their groupings. And in fact, some of these will be candidate buckyball, but again, this is by now well known. This work was done between 1980-81. I published, my PhD was 81, and then 1990 I published this idea of the spheres. 95 I did the polytopes. And so essentially looking at very old work. And I'll show you the new work later on, yeah. And these are a little bit more problematic, where the skewing adds, I think, 3 more. So I haven't shown the polygon. If you pull in the polygon, you'll get snubs, I think. And you're traveling along the vertices of a cube. So if you add one more direction to it, then you get the 4-dimensional cases, of which the cubic lattice or cubic honeycomb is a degenerate case, and that's purely Euclidean. And the same idea works. What happens is you have 4 generators, and they lead, 4 generators lead to a 4-dimensional cube. And if you go to the next dimension, 5th dimension, you'll have 5. And go to 5-dimensional space, and the number of possibilities will go 2 to the power n for every dimension. So this will be 2 to the power 4, yeah. Okay, same. Now, interesting thing here. Oh, sorry. Yeah, okay, is that okay? So same idea of a continuum of morphing works here as well. This is just a random path through the hypercube. It's just not systematically done. And these are all the cells around the fundamental region. And in fact, I showed this to Coxeter in 1985 in his office in Toronto. And his comment was, but there are duplicates. And he was referring to this and this and that, duplicates, this and that, and they're topological duplicates. And that question did bother me, but later on I found the answer after I left his office, so I didn't have the answer. But I asked him, okay, but then why are the colors different? And he had no response, but that question, I already had an answer from Cyril Smith. I showed, in 76, I had the first diagram I showed to Cyril Smith. I said, look, the colors work like color cube. You add red and yellow, you get this one, and you add blue and yellow, you get green, etc. And works like this for shape. And he just smiled at me and he said, listen, as a colorblind metallurgist, I don't care a damn. So that took care of color business. But then I've had another idea then I showed this to Coxeter. I said, wait a minute. If that's the case, why is it that if I take the metric, these are all the fundamental domain of the packings, and if I take the metric here, this size, if you take this height, and then I have 2.4 here, I have 2. Those two will add up to this one, which is the 111 case, and so on for all the opposites. Why are they coming in these complementary numbers? And this will work for the 120 cell, it will work for the 5 cell, it will work all the way through. And then I think he agreed this seemed right here. It's sort of an indirect acknowledgement that this was correct. And it'll work here as well. If you do the numbers of this thing, they work exactly the same thing. But here's the answer to his question. Why there are no duplicates here is because the symbol is non-palindromic. And the 4-3-4 is palindrome, therefore. And same thing for this. And for the 24 cell, and so on. And you can start doing the way I did for the polyhedra. You can go through lattice after lattice after lattice, and you can navigate through this whole world. And then you can add other features to it, for example, removing colors from it. And then you start, I'm adding here, there's 6 colors, I'm removing them. Then you start to get what are called infinite polyhedra. And their symbols become even more dense, and you're taking these number lattices through more complex spaces. And here, these are, for this case, one group of infinite polyhedra, and the ones Coxeter and Petrie discovered early on are these two here. And for each number, there'll be 3 sets like this. Not many possibilities. This has the most possibilities, but then it's analogous. It works all the way through. This is for the hypercube, or 4-dimensional cube. And then you can start again putting them in lattices and so on. And a very interesting case where this is 2, when you essentially are having 2 polyhedra, one inside the other if you want, where the cross-section is really a diagon. And then if you do their Schlafly symbol, it becomes a nice number lattice. So this is one example. And if you look at the interiors, you can actually code all of those like that. And you can see the diagon is here with only 2 points. I made it a circle, but it could as well have been the more classic diagon. And then I could add to this curvatures on the edges. There are 4 edges in this one, and there are various ways to do them, and you get all the curvy versions. And interesting that this, which was a self-dual, is no longer the two cells become different. And Zoran, can you do this? So that adds more formal possibilities to this world. And this leads me to now, so what? I mean, this is, and from our point of view in design, it gives me a starting point for, let's say in this case, György's one example, Portico A, his finest example. And you can see that if you model that like that, and then you start changing proportions, then you start tilting them, you can go through a sequence where this is the final result, and that view is looking from this side here. And in fact, we did an animation. It looks like this. I don't have the animation, but you can see that it's pretty much very Romanesque in its very Platonic state. But as you change proportions, and then you bring angles in here, and finally you get the classic view of György's Portico. And likewise, it means that if this one goes there, I can index those, and I can take this one, go back, and regularize it. I can take this one and go back there and go there. And then what happens is that I start to get these, which make a full family. So then what you can do is that, okay, here is one piece of architecture, another piece of architecture, another piece, and they all are like a continuum. So that gives me a different model, different way to look at it. Zoran, please. So this is a simple, very simple forms, because György pretty much had simple forms compared to what's possible now. But again, I think I would say he was the first topological architect for the reason I'll show after this. And then it was extended by György in 1959, 60, 61, where the non-orientable surfaces entered, then rediscovered in the 90s. That's like the history of this. So we can add some more features to this thing. So if you look at this, the cell, which is the short surface cell, and you look at this like a plumbing connection, it has 6 directions, and you can find the plumbing joints for all different directions, and they all map like this, and I've added 6 more dimensions to that, and you can start to now correlate the facade of Casamila to this thing where, let's say, this node is really that node, and, wait a minute, 5 is 5, yeah. 5 is over here. So this node is that node, and so on. And if you look at one more interesting case is the balcony here, where now these nodes are becoming that one here, that one, and this joinery is over here, this is a T connection, etc. So you can map one-to-one in that sense. And so this is kind of a regularized version of Casamila. So it gives me hope. But again, this is not Casamila. You have to do all the morphings from here on. But it gives me the foundation. So now I can say, wait a minute, maybe this is right. You know, we started with mathematics, but now we can go into design. And over a period of time, these things might start to become more complex architecture. Tomorrow, at the Family Day, I'll be showing this group of tiles. I call them pentiles. And really the motivation was that what you saw in György and the early thing, they're very simple examples. But I was wondering, what about the other dimensions? Because I was dealing with hypercubes, I wanted to build them. And it led to this simple, in 1981, this discovery that if you take a hypercube, this is a 7-dimensional cube, and I wanted to build it. So I had to break it down, and you break it into tiles, and the remarkable thing was, if this is 7-dimensional, 7 vectors, then the only numbers that are possible are 1 to 6, 2, 5. These are the only decompositions of number 7, therefore there are only 3 tiles, and therefore Penrose tiling, which is for 5, is only has 2 tiles. And this was I presented this at Bielefeld for the first time in 1985. Andres Press was kind enough to invite me, and that's the first time I presented this idea. And you can see this is Penrose, classic Penrose tiling, and so on. You can go. And then you apply this to the simplexes. Same idea works, that you have any number, like number 6, can only be broken up into 114, 123, 222, and those are only numbers that are with 6, therefore there are only 3 triangles possible from this. Likewise, you have a whole infinite table of triangles that are coming from there. And you can index them, you can map them now. 3 sides mean 3-dimensional space, and it looks like, and it is a continuum, and those numbers are really, you can see they're continuous numbers. Though I'm showing a number changing to the other, it's really going through a continuous change. Because we don't know how to show the decimal points without making very long numbers. So every number sequence then has a shape associated with it. And those tiles are derived like that. So I can type in a bunch of numbers, I'll get some shape with it. So take this one. A little bit of trick here because it wouldn't morph like this quite easily. The edges have to change length. But if you think of this as projected from higher dimensions, you're really taking, oops, sorry. You're really taking these 2 sides, which if this is 1 and that's 1, you're going through a diagonal stage. So that's root 2. So it has to change its length. But in its projection, this is possible. And then this gives me the idea that, which I just mentioned, that for every number I can find polygons, and the number of sides or number of angles is the extent of the length of this number. So dot is the starting point, and these numbers go according to the earlier diagram I showed. And then you add one more idea to this, which is I can make curvy version of this by rounding off the corner. There are many procedures, many algorithms for doing that. I just take one and stage 6 in the curving of that leads to this kind of thing. And you can apply, since this number, really not all the number sequences are closed into polygons. In fact, most of them don't. And you get, I was looking at prime numbers, they're not very interesting at this point. But then they give you all these self-intersected lines, etc. And these then become units for fractal edges and so on. And then, this is 92, I discovered that what you could do is you could start building with these tiles different surfaces. So it really became mapping of these aperiodic tilings onto various surfaces. And this was a discovery at that time. You can do this on a short surface, or you can make membrane structures like that. But this turned out to be very interesting. We did some, the way it's shown with ball and stick, this is not going to work. You'll need a triangulation here. But we did this with panel. We did an analysis recently, which is not published, but I'm going to announce a little bit of the result. This was Robert Otani, the engineer at Weidlinger Associates in New York. And we found that this, if you compare this to Bucky-Fuller's dome, which are a model of efficiency, and you compare almost like apples to apples, that, and you keep the number of vertices, we have about 1,400 in both cases, that if these were made out of panels, like a full triangular panels, like plates, then this was slightly better than Bucky's domes, which is a surprise to us. We didn't know that. And the various sculptures are now coming out of that work from the 90s, which are these. And we can start tiling the spheres that way. Interesting that then there was this commission which is on the MoMA block. MoMA is right over there, two buildings away, 54th Street and 6th Avenue intersections. If you go there, it's smaller than I wanted it bigger, but it wasn't possible. But interesting thing you notice here is that these things essentially are a non-convex hexagon. And you know, you can't tile a sphere with hexagons. But at least if you make them non-convex, you can. So here's a sphere with only non-convex hexagons, which was interesting. And I've done with 8-sided, you can do it only with octagons, only with decagons, and so on. And if you do odd numbers, they require another introduction of another length sort of thing. And you can keep continuing and keep adding more and more things to it. So I'll just give you a random sampling of more classic things where, in this case, you're just mirroring a face around its edges, and you can do any combinations there. Or then you can add the things we saw in polyhedral transformations, that these things can also morph to each other. And then we can try these things, which we do in the classic architecture design exercises was in the 70s was the 9-square cube, and you're making compositions out of it. And again, this thing adds maybe, if each is a different dimension, then of course you've expanded the space much more. And the cellular automata are just one step away. If you take Wolfram's 1D automata, he had 256 rooms, and if you map them, they're 8 generators, and they'll fit perfectly nicely there. And there is this famous rule 30, which is shown here on a cube, which is inflated into a sphere. So the proposal then is that it seems possible that you can maybe take form and start to break it down into groups or families of parameters. So the parameters don't overlap with the others, they're independent, and they come in different groups, which are shown by these branchings. And I've gone through a few of these, and I'm calling these independent ones as a gene. So then they become the morphological genes of form. And if you put all of them together, you'll get something like the morphological genome. That's the underlying driver here. Nowhere near, I think I'm just scratching the surface, but this is the beginning. Can I go to part 2, please? I'll show you the new work at the factory, which is the epigenetics component. So this work is just an idea, but I thought I'll show you. Okay. In 96, I had a connection with the factory, Milgo Bufkin. They make fine metalwork, and they were interested in doing something. Next one, please. So it began with, next one. Oh, sorry. I was playing with these in the 70s, but then 25 years later they came in handy, that I went back to these things. These are well known. But this could be used as a new system to form metal. So what you do is you put the slits in there, then you form it, and you get this thing. So I would suggest that it's very interesting that if you start with a flat plane, you have these squares there, and then there's a dome, and these things are twisted. So if you map the movement of each of those, you really get these things are going through curved space, twisted curved space. That's what's being formed as its trace geometry. And I would say that this one is the third in the lineage, the first being György's hanging chain models, where he would hang them, they would make catenaries and freeze the form, turn it upside down, and he got his vaulting. Second improvement was Fraiotto, instead of lines, you had a whole grid, a whole mesh being hung by gravity, and then they were frozen in form and turned upside. But in this case, what he did was he had a flat grid here, which was jacked up, and then they slide. These are all joints here. They slide, and you can tighten them to the curvature you want. So what we are doing, I believe, is a third, because what it does is slightly different. It starts with a rigid material, which is steel plate, we sort of weaken it, but then we get a rigid form. And the behavior is plate action. They're like plates, but the points are hinges. We don't have any... Zara, can you see that? So what we did was one experiment. We have many ways of forming this thing, and I've been asked by the factory not to discuss proprietary things because they've invested a lot of money in this. But we'll show this in honor of Einstein's work, that we took a steel plate and we rolled the ball on it, seemed to do nothing, we rolled it again, it gradually started curving. And what we did more, it started curving more. And finally you say, hey, wait a minute, this is important. We didn't know this, and we started recording it. So what you're seeing is a record of the last few minutes of this thing. And you'll see here, interesting, that underneath, there we go, it is a dome. It is a dome. So weight has been used to shape form. So it's a new way to shape metal, new way to shape material. And these are rigid forms. So that is the invention, actually. And we try to scale it up. And these are epigenetics because these are coming from force which is outside of the genetic we're talking about. Therefore, epigenetic. And you know, steel plates come in a certain width, 4 feet, 5 feet, 6 feet, and you want to make larger, you have to seam them, and look at the seam here. We were able to seam it, and it worked seamlessly. Wasn't obvious at all. It could crinkle there, it could bend there, it could do all kinds of, it worked perfectly in the first time. So this was a great surprise for us. And of course, I show this for fun because everyone in the factory gets excited. We've never seen anything like this. You go underneath, look at the lights, look at the openings, because it was solid, flat sheet. And they did this thing. It's sort of kind of magical. I hate to use the word with scientists, magical. But I think Arthur Clarke's definition that magic is any unexplained technology sits well with me. So so essentially then what happens is, combined with this method, steel plates and forming these becomes a tailoring problem. You can essentially tailor any form, join them together and form them, and they come out seamless. So I'll show you one case. We make the frame, we insert the laser cut, these are all patterns there, these are the seams, we form them, and this is the object, quite heavy. It's heavy largely because of the beam outside, which we want to get rid of, and we will, but less control, but it's possible, and more investment of resources and technology there. And it's still like a empirical art. We're just feeling it out, and it's not smooth here, and fix it here, or that kind of thing. All pretty much like old craft. And the finished piece looks more impressive and a very proud team. They all get so excited. So this deserved a photograph. And just to show you some in-process photographs, because when we work with them, all the fingerprints, everything, and eventually it gets all cleaned up. But I want to show you how beautiful the seam is, that we are able to produce these compound curves with negative curvature very cleanly with sheets of metal. And we've gone up to a 1/4 inch thick steel. You wouldn't believe it, that it's possible with not much investment of technology to form it. And in fact, a small dome like this, a person can stand on it, so it'll be nice if you want to make a large one where a truck can go over it. And I believe it will. But we don't know. Structurally, no analysis done, but I'll show you soon. So they are becoming like sculpture experiments. This is a small maquette. It's about this size for a large wall, 20-foot wall sculpture, which will go up in the next, hopefully in the next few months. Some more. You recognize in the aperiodic tilings different nodal conditions for 7, 6, etc., 8, and so on. Talking about gravitational waves and things, this was done 10 years ago or something. It's always a challenge. But again, here's an open-ended, we don't know how to form it. Obviously we made it. And we're thinking of all these balls rolling in parallel, maybe some going underneath. It just became haywire, but we made it. But our dream is that we'd like to use these technologies on a larger scale and make it, but we haven't had a chance, basically. I think in future, I think nanotechnology probably will end up at a point where we can control self-shaping of matter by coding it, but that's not my area. But that's where I think it's heading in that direction. Perfect cylinder out of the same method. Torus not too successful, but it does it. Proof of concept. Perfect hyperboloid. This is Robert Raisin's hands. He did the tooling and everything. And this is one of the most perfect hyperboloids I've seen in physical material. I mean, imagine, it starts with a flat sheet. And you can undulate them and so on. This is a sphere, but I didn't show the full thing because it's like oddly formed. It's not so beautifully done. But at least a proof that can happen. So you can imagine spheres pulsating and so on with the openings and closings and some amusing design applications for that. Or with lines of forces, or as modules of infinite continuous surfaces. So this is going to, if you repeat this, it is going to produce a minimal surface that goes all over space, yeah. Space filling, as you call it. And various tilings out of these, periodic, beginning of a periodic, or curving as boundaries possible. Those are all on a flat plane. Very hard to take them out of the plane, but we were able to do it. I mean, you can imagine, because you are forming it and the edge is expanding. It's not easy. Or give it constraints to give structural surfaces so they become stronger, so that these have a scallop section. If you cut it, it's like bumpy. Now, here was the beginning of, which is the direction I'd like to go in, which is it starts to shape itself. That'll be, to me, in other words, the designer is out of the picture, and objects start to shape themselves, pretty much following nature's processes. And that, to me, philosophically, is the way to go. And I think the future might be heading in that direction. So here what happens is we had one place where we had no cuts. So that gave a constraint. And we formed it, and it produced all these things by itself. Now, remember, there's no molding used, there's no heat, it's just cold metal. So this is a big surprise, and we didn't know why it's doing that. And they remind you of beetle shells and crabs and things like that. Natural, because all you're doing is by controlling the openings, you're giving it strength. This is stronger than that area, and that's where the strength is needed. That's like a beam, it's like an arch there. So I think nature might be using something, but again, that's a question for developmental biologists and so on. But you feel that when you see this, it's sort of shaping itself. So this was the first kind of self-shaping. Another one. And here we got the answer why it's doing that. We pull the sheet, and since these are rotating, it's going to expand that way. But when you pull something, it shrinks this way, so they're in competition. Therefore, the only way it has to go is in the third dimension. So you're going to pull it, it's going to wave. So suddenly we got our waves formed by just pulling. And this expansion. So this was a huge surprise. And in fact, my colleague who was working with me on phone, he said, before we did this, he said, I know, I think what's going on here is it doesn't know where else to go. And I think that captured it. It has no other way to go. This is the second type of self-forming we have, where because of its topology, this is the dual of Penrose tiling, in fact. What it does is they start to wobble and undulate. And it looks like that. And I don't think you can see, I'll show you a close-up. And a big surprise to us, not clear this would happen, that we had, in a way, discovered an optic solution to cubism. So you stand in front of it, it just fractures your faces in all kinds of ways, including thing inverting. We had left to right, juxta, up to down. All of those are possible. And then I went to look, sometimes I couldn't find it, but sometimes you do. So it's all transitory, but it's very beautiful that this happens, and totally unanticipated. We have no idea this will happen. So here's the beginning of another piece with kind of irregular, but they're not. They all are very ordered structures. They look irregular, and it forms like that. And a close-up of one of those in the family is like, now it does all this stuff. So again, this is the second category of things shaping themselves. The third category we found was this very simple experiment where we said, okay, or I said, okay, that we're going to keep equal area of metal. All we're going to do is change its boundary. So imagine this thing is as big as this, so it's sitting next to each other. We had 5 cases, and all we did was the boundary. Here's a circle. Here's like, it's a super quadric. And this is heading towards a square. Okay. Now what happens is that as it's becoming a square, this is becoming crumpled. It's self-shaping itself. It's like crumpling itself. Big surprise. Didn't know that. So there's more boundary in relation to the area. It does that. So here is one of the videos. It's a very fast laser cutter, very large. Here's the first evidence that we have really weakened the material. It's wobbly. But after forming, it becomes rigid. Big surprise. So it's like an oxymoron. You weaken to strengthen, but that's what it is. Here's real time with a GoPro. We're showing like a quadrant of it. This is the speed at which it forms. They're surprisingly beautiful because we haven't touched them, untouched by human hands, by natural processes. It's just so beautiful. And they just... Oh, here, this is very important. This is real-time stainless steel behaving like fluid. There we go. All the crumple, rimpling you saw, this is happening like this. I think the first time ever. That's the crumpling after it's frozen. I have to acknowledge Bruce because he's been supporting all the work. He's the owner of the factory and a huge, huge thing for the last, since 97, we've been doing all this stuff. Some of the pieces, here again, totally untouched by human hands, only force making it. Here's the what is the fourth kind of self-shaping found. We had these things and we formed it and it started making openings of variable sizes, which in design you'll be killing for this because you need every opening to be adjusted to the environment you're dealing with. So the variability has come so important that we want it tied to a forming process, but we haven't mastered this because sometimes it formed this, sometimes it formed that. But really, it feels like an organic skin now. And some sealing systems, etc. we've done. And the last experiment I'll show you here is in tensile architecture, we have the two, there's of course the tension mesh or membrane, but then there are two features. There's always a pole which is going up, and then always these counter pulling to the ground. So these are the anchorages. So you need to tie it here, you need all the edge cables, and you need this one. I was wondering if we can get rid of them. So here's get rid of the column. The pole is gone. So you can make any surfaces that will be rigid without the pole, which always interferes with the space inside. So now we can make a tensile-looking surface, but it's rigid, out of metal. And here is a case where the boundary is gone because these become self-supporting. It's a rigid structure. And of course, we'd like to build some pavilions and things like that. So here are some experiments along those lines. This is rather remarkable. You can imagine an area like this, which is this one. I forget. It's quite wide like that. And if you take stretch fabric, the one we use in stockings and things, and you put it here, and you try to put a pole underneath, it'll probably rise up to this. And you can see what we've done. We have outperformed stretch fabric with metal. We are going to 18 feet from something, I forget the size, I think this is a little less than 6 feet. So we're going 3-4 times the size. Quite remarkable. Didn't know that. Here's an attempt to make an opening inside, and here's a sequence, of how it goes through. And here's the piece, those are studies for this piece, which is upstate, and is remarkably rigid. And this doesn't collapse by itself. Now, once we formed it, it's there, which we did not know. Sorry, please. And here's a little video. This is a real-time clock. It takes us about the last bit, it took about half an hour to make it, but then we stop and start and we check if it's working, it's breaking or whatever. And so we record all of that, then we edit to keep only the forming part, remove all the stops and starts. So you can see what's going on. It's forming very rapidly. So there, in less than a minute, we've gone 12 feet. So we're heading towards instant architecture, essentially. So if you have emergency shelters, you can bring it to the site, raise it up, and you're done. Not there, we haven't done the experiment, but that's the idea. And something you might find interesting is that we've done so many experiments. There's a flat one, there's like a conical one, there's like a pseudosphere, there's a sphere, and elongated ellipsoidal forms and so on. So it looks like if we just change the density and the strength of the mesh, we can get from Euclidean to non-Euclidean. And by instinct, simple, that nature doesn't know the difference between the two. It just goes as a continuum. And these are examples like that. And here's a case. Sorry. You can almost see an organism. Here's the final piece. And the idea was, what is minimum architecture? I think it requires three things. You need space, you need surface, you need opening. That's it. So architecture is a minimum 3-gene operation. And take away any of those, you will not have architecture. You'll have something different, but not that. So here we're not counting the floor, though we could have done floor as part of the thing. Mathematicians will call this like two surfaces, one here and one on top, like a dihedron, but it's not.
Christoph Fenyvesi,
conceptually, yeah. But we could have made it as one piece. So the point was made that, and it makes me wonder how, like this is the shape of the eye, which is the window really. If there's the equivalent in morphogenesis in biology and development, where there's a equivalent of how, because if we start as a sphere, then we're getting all these openings and then how somewhere some puncturing is going on, some rupturing, something is going on. And I don't know if something is known about that in actual organisms as they grow. But I'd be curious to know. This is on its way to the factory, or to the installation. And last few only computer images in this are these. There's a proposal to build a whole pavilion. We bring it to the site and just jack it up. Did not happen. Likewise, similarly, we'd like to build these things, or like that. And my last image. Okay. Thank you.
Thank you very much. Thank you, Professor Lalvani. There is some time to put some questions to Professor Lalvani. Yeah, please. Let's start with
me? Him?
Oh, sorry.
I see. I'm supposed to talk into this now. I was just wondering, some of the forms are very suggestive, like the last one you showed is reminiscent of some comments earlier today about the Einstein-Rosen bridge, you know, the one universe.
Yeah. Sure.
The other thing, I was wondering whether you had interacted with any structural engineers who have a deep knowledge of the strength of materials and how things get affected by various stresses, so as to perhaps be able to control very precisely the shapes that you have.
Yeah, this is a difficult one because engineers don't work for free, we have to pay them. And this becomes, since these are not funded projects, they're being funded by industry partners, we're waiting for projects where we can actually do that. So yeah, it's in the works. We've done one experiment with Robert Otani. Now we're going to be working with Leslie Robertson's firm on some of the projects, but we're just waiting for projects to happen when we can give them a stipend, because we have to. Because we don't have academic, at least access to academic structural engineers. Pratt doesn't have it. So all the people there are either professionally working outside, they come and teach a course and that kind of thing. So we're not in a research environment where we could easily call an engineer and say, hey, help, or a mathematician. We desperately need all of that. We need a mathematician, computational programmers, we need all of that, of course. And this is, remember, it's being done pretty much brute force thing. It's just being driven without very high-powered stuff, because the tools are way more powerful than what we use here and what we need. You know, you'd love to. Sorry, there was a question.
Yes, up here.
Yeah,
First of all, wait for me. First of all, from beginning to end, that was one of the most inspiring talks I've seen. I was just wondering, have you considered the expansion coefficient due to heat from different metals, and possibly fusing different metals together with different expansion coefficients so that it responds to sunlight and membranes for facades and whatnot?
Can I shut it off?
Right. Okay. How do I turn it off? Oh, there we go.
Are you off?
Yeah.
Okay. Yeah, can you hear me? Hello?
Yeah.
You can hear me? Yes. Okay. The answer is no. We haven't. We're working with steel and stainless steel and so on. And for the MoMA piece, I said we should do titanium. The moment you switch materials is a whole new learning, because these are experimental technologies. We don't know how they're going to work. And titanium, every time we tried to bend it, it broke. It's brittle. To find the right composition, Bruce, who's a metallurgist, is the owner of the factory, he had to scout around companies to get samples, and finally the MoMA piece, we were able to make it out of one piece. It's all this curvy stuff. It's folded titanium. First time ever anyone's done that, you know. So whenever you go outside into new, it opens up a whole frontier. And yeah, I suppose if you have unlimited resources, you might. Remember, this is being done in a factory. It's not funded. That's like a patron type situation where you sort of, the factory is working, producing projects, and these are pushing in between, but everyone loves it. So they just love working with us because this is a lot of fun.
The possibilities of that are incredible, though. Just, I'm thinking.
Oh yeah, absolutely. I mean, we don't. I wish we had the access and this. It's the same question. How do you go beyond what you're doing? And it's all restricted by available funding. That's where it comes down, not lack of ideas of interest. And also, I'm kind of a purist, if you wish. I like to stay with one idea and run with it. And the moment you try so many different things, you get so scattered. Already this is, in a way, all scattered all over the place. But over a period of time, it's all going in one direction. And my hope is in the future, in fact, speaking of collaborations, my hope is in future the first part and the second part will be joined together. And I think synthetic biology is going in a different direction. But there might be a way to tie shape coding with DNA sequencing. That hasn't been done. I think it might be possible. And the only clue is Leonard Edelman's the DNA computer, where he solved the conics problem. He was actually coding with DNA codes the different conditions, the 7 locations. And if you could do that, why couldn't we code shape? So then you produce essentially an ASCII code for shapes. You know, so many A's is this shape, and you start making a whole code. And then you have biological processes that you have on and off, like stop and start. Those are all known. And you can then have biology start to make all this stuff. That'll be my hope. So coding will be tied at some point to biology, nanobiotech, or maybe even pure, without nanotech. Don't know. those are outside my area, but I think we are so interested in that. And DNA origami is not quite there, meaning they are doing it, but it's in a way kind of losing its purpose, meaning now the DNA origamists are becoming artists, basically. They're producing for the sake of it. So you see this tensegrity DNA origami structure, which is so out of proportion, just seems like, why do this, you know? So it's losing some of its, but there's excitement that you're able to code sequences to produce pretty complex forms. So that's the exciting part. But I think it's in the early stages.
I just want to add one more thing. There's one architect. Okay, one architect who Doris Sung, who has done that expansion and contraction.
Yes, I know that.
You should. I would love to see a collaboration between that. Anyway.
Somebody else has mentioned the same thing. Yeah. Thank you, though.
You can discuss later with each other. Please, this one.
First of all, thanks for this cosmic experience. And I wish to ask you something that relates to the architecture thinking, human thinking. Because what you're doing, in my opinion, is interacting with infinity. And it's always full of surprises. You mentioned many times that you were surprised to see how shapes self-organize. There is a fantastic theorem by a Russian logician, contemporary one, Larissa Markova, who has proved that there is a continuum of non-classical logics. That is, there are more logics that will always be logicians, even if time were to be infinite, to get them born. As far as I can get it, you prove a similar fundamental result, methodologically speaking, and dealing with a continuum of forms. You prove that they correspond to strings of numbers or some kind of codes, numerical codes, and they're a continuum. Well, it's always very interesting and challenging to know what kind of infinity you get. There is innumerable and there is the continuum. Do you claim, that would be fantastic in my opinion, do you claim that what you produce, what you can generate in terms of art and the underlying logic of this will be a continuum of such forms?
Yeah, that's the...
Thank you. Thank you.
Well, this is a deep question, which I think all in mathematics, physics, and philosophers, the difference between the discrete and the continuous is a classic problem. I don't know the answer. My intuition is heading all in the continuum direction, but then I also know the binary logic exists. For example, if you take logic as in classical logic, the 16 operations, in 1982 I put them on a hypercube, and then I can see them moving around in a continuum, so that produces a continuous logic. So in other words, if you index them in four-dimensional coordinates, the space in between, and I didn't know about fuzzy logic and that kind of thing, whether they think it came around the same time. So my intuition says yes, but I haven't found it to be universally true in some of the experiments. Like cellular automata is completely discrete. I don't know. I'd like to think that it exists, but so far there are probably 2 or 3 examples where I haven't found it to happen. That's why the introduction between number 2 and 3, I put in those fractions and the real number. That was the attempt to do that. It's a hope.
First, turn it off. I think I speak loud enough to hear.
All the things that you produce are beautiful. I love looking at them. So there's some aesthetic quality to this. I don't know why. You mentioned the 4 nucleotides in biology generating all sorts of forms. That is true, and that is well understood now, because although the alphabet is simple, what is complicated is the history, the evolution. Now, I think simpler model may be the snowflakes. Snowflakes are formed with the H2O, and as it falls down from the sky, it forms millions of different forms because its trajectories are different. And it seems like you have a similar thing. You have a plate on which you can make patterns, infinite number of patterns, which is arbitrary, and then you have a gravitational force acting on it. So I'm just wondering whether you have a new alphabet, new language, material plates, the arbitrary signs written on it, acted by gravitational force. With this, you may be able to produce infinite number of forms, just like there are infinite number of snowflakes.
Yeah, possible. Because I think one of our interests is exactly that. Because in design, the world has moved from the industrial model, which is the industrialization has produced Hello? Yeah, good. Can you hear me? Yeah. Industrial production methods have, due to economy, have moved it in the direction of everything identical. So I have this cup, you make millions of these cups, it's cheaper to do that. And one of the experiments which I haven't shown here was we did it for Miami design. We took a platter, a steel plate, and we called it a fruit platter. We cut it with laser. It had 300 holes in it. And we formed with the same method of forming, not this, but a different one. And the pattern was generated by numbers. So the holes had a distance, and the distance was regulated. And the distance was a continuum. So I could have gone to infinity. And then we produced an animation where the pattern was changing and there was a number there. And the idea was we showed 1,000 of them, and somebody wants a platter and say, oh, stop there, give me 967, and we'll tie it to the factory will ship it to you. So you pick your own number, we ship. But the message there was that if you can tie it to the simplest, in this case was one number, tied to infinite solutions from one number, changing one number, then you practically have produce a design unique for every person on the planet. Simple. And that's a design goal. Why should we give identical things to everyone, you know? And then to prove that, and the answer is economy of production, okay? It's called economy of scale. I think what we did was, we proved that our platter, even though each is different, it will not cost more than, normally if you make a unique one, it costs much more. Here, all of them cost the same. So we destroyed the economy of scale argument. And the way we achieved that, because I didn't want to trust the manufacturer to give me a price. He'll say it costs so much. How do I know that? And normally they don't tell you how they calculate how much it costs. This is like trade secret. Businesses don't tell you why this thing is costing so much. They don't tell you. So I didn't want to do that. So I said, can I put it in the design? So here's what we did. We made sure that, since it's laser cut, a laser is a one-dimensional tool. We made sure the cutting length of all the platters was the same, and the pattern was different. So if its cutting length is identical, or near identical, they're all going to cost the same. So we put it in design. And so our goal was to, produce infinite variation. So that whole idea of what's called mass customization is at the heart of this, which is the same thing which I started in biology, which is how come all of us look alike and we're all different? That's the design challenge. And we're trying to achieve it out of either coding or through processes. And yes, certainly we can make these sculptures, like I have a couple of pieces there, for each series we can make infinite of them. Certainly, that's our goal.
Okay, thank you very much. We run out of the time, so we have no time for more questions. Before I would express our thanks for this very shocking and excellent presentation to Professor Lalvani. I would like to announce that the city of Vienna, or more exactly the cultural department of the city of Vienna, has a lecture series called the Vienna Vorlesungen, and thanks to our host Wolfgang Hofkirchner, with the help of our local organizer Renate Quenberger, the city of Vienna invited Professor Lalvani and his today lecture to be included in this famous lecture series, in which many outstanding scientists and artists read lectures for several years. So this lecture was sponsored and honored as a sponsorship by the city of Vienna, and it was recorded, and the recording will be used probably by one of the local channels of the television set of the city of Vienna. And we are invited, thanks to this excellent lecture by Professor Lalvani, to a reception a little farther from here, but in a very, very famous dining out area of Vienna. I will ask Annette to tell us in detail how we will get there. We will go together, but she will explain you how can we reach the place. And before she tells us this, I would like to tell that also the International Symmetry Association appreciated the contribution of Professor Lalvani to the work of the association, and his offered lecture here in the festival and conference program, and in the Vienna Vorlesungen, or Wiener Vorlesungen lecture series, and I will have to give over this honor to our new honorary member, because your contribution was very important to this lecture, and you are the best co-worker of Professor Lalvani. So I give the floor to Annette.
Yeah.